How to orthogonalize a basis using the Gram-Schmidt process. The process of orthogonalizing a basis revolutionized the field of linear algebra because it allowed complex systems to be simplified in a way that allowed mathematicians to discover more properties and relationships within linear systems. Panaja Vyshilevsky, an esteemed researcher, suggested in his 2013 Numerical Linear Algebra with Applications textbook that much of what we know today about complex linear equations would have been nearly impossible to discover without the Gram-Schmidt process. The Gram-Schmidt process is the procedure for orthogonalizing a basis and is named after its two creators. I took linear algebra last semester and was disappointed that I could not find a video that adequately explained the derivatization of orthogonalizing a basis so that I could conceptually derive the formula versus memorizing it. After referencing two videos, both titled The Gram-Schmidt Process, made by Khan Academy in 2012 and a University of Texas math professor in 2013, I will show you today how to derive and use the Gram-Schmidt formula to successfully create an orthogonal basis. To understand this video, please make sure you already are comfortable with finding inner products, like dot products, and can perform basic matrix operations like reduced row echelon form and finding a determinant. When starting a problem, it is important to first check that the set of equations you have do in fact constitute a basis. To remind you, this can be quickly checked by ensuring that the number of equations in the system is equal to the number of unknowns in the row echelon form of the system, or that the reduced row echelon form is the identity matrix. Alternatively, you could check that the determinant of the system is non-zero. To create an orthogonal basis, it is also important that the system contains at least two equations. The first step of the actual process is to number the equations numerically, preferably so the equations with fractions or square roots are last. Now the first vector always starts as a reference vector and is equal to its orthogonalized version. The second vector can be broken apart into two pieces, the part that is projected onto the first vector being parallel to it, and the second part which is the piece orthogonal to the projection. As you can see, orthogonal vector 2 is our desired vector to complete the orthogonal basis. To obtain OV2, we simply need to subtract the projection of V2 onto OV1 from V2. Remember that the projection can be expressed as the inner product of the vector being projected and the base vector over the inner product of the base vector with itself. In this example, we're going to use dot product, so the equation can be written as follows. Now plugging in our vectors will give the vector 6, 4, 5 minus 1, 1, 1 times the dot product of these two vectors over the dot product of 1, 1, 1 with itself. This gives the result of 1, negative 1, 0. We have now found two orthogonal vectors. For the third, we will have to draw in 3D. As you can see, vector 3 can be broken apart into three pieces. There's the projection over OV1, its projection over OV2, and then the orthogonal piece which is not parallel to any of the prior orthogonal vectors. As before, subtracting these unwanted pieces from the orthogonal vector will allow you to obtain OV3. Using dot product notation, we can now write the equation as follows. Notice that the Gram-Schmidt equation calls for the orthogonal vectors, not the original ones. A common mistake is to complete this formula with OV2 instead of V2, since the first projection V1 and OV1 are the same, so it causes no difference. However, a projection of V3 onto V2 will result in a vector piece that is not parallel to any of the prior vectors. This is why only the projection onto OV2 is wanted. Plugging in the vectors will give the following. 1/2, 2, 2 minus 1, 1, 1 times 9/2 over 3 minus 1, negative 1, 0 times 3/2 over 2. After simplification, watching out for negative signs, we will find that OV3 is equal to negative 1/4, negative 1/4, 1/2, concluding our procedure and resulting in an orthogonal basis. You should now be able to derive and utilize the Gram-Schmidt process to orthogonalize a basis. Congratulations! You can now do something that Vyshilevsky noted took Gram and Schmidt over 3 years to derive. Here are the references used for this presentation. Thanks for listening.